Good morning, good afternoon, wherever you are in these virtual talk times, which are difficult to get exactly right. So I'm here to talk about vision and imitation for robotics tasks, and let's get the setting right. So the setting is the following. I mean, we are trying to exploit vision for guiding action. And this could be navigation, it could be manipulation. And I'm going to give you examples of both. Uh, so we can try to train policies for this. So there is a visual observation, and then we guide action. So in this case, this is a navigation task. So actions are of the type move left, move right, move forward, that sort of stuff. And how do we do this? So the question is, what is the visual system good for? So one thesis we could have is that we directly connect up the pixels to talks, right? That more or less amounts to a statement that nothing that the computer vision community has done for the last 50 years is of much use, because obviously we are not making use of any of the representations or abstractions that have been developed in that community in the last 50 years. So I, as a person who has devoted so much of his life to that, cannot possibly like that. Well, that's not a good reason. Another reason is that if we look at biological systems, we find that a significant portion of the cortex is devoted to vision. And there are many areas where there are retinotopic maps. And somehow they are building representations that must be of some use for various action tasks, because ultimately the evolutionary value of perception is only in the sense that it guides actions. So that's the problem that I'm trying to study. Now, so I have to start with a critique of what the current end-to-end learning approaches, the ones which go from pixels to actions. What's the problem with those approaches? So here are some claims. The claims are that these models do not generalize well to new domains. Yes, you can, with enough data on any specific task, one can do quite well. Secondly, we are treating each task completely independently. So there is really no transfer in the vanilla version of this problem. And this is not right, right? I mean, humans have the capability that we can do any task reasonably, fairly quickly. Okay, so my favorite example for this is learning to play tennis. Okay, I may never get as good as Nadal, but when I go to a tennis court, somebody gives me a racket and a ball, and in one trial, I'm ready to start playing tennis. So we need to have that ability, and yet also the ability that you can subsequently keep improving with practice. Okay, so this is a critique for raw pixels. This is the philosophical position that we take, which is that vision should provide a useful abstraction. It should be robust across many conditions. It should be generic enough that it does not need to be completely retrained for each new task. So I'm not going to go all the way back to classical robotics, because classical robotics had this approach where they had this abstraction that the world consists of objects. The objects have some rotation and translation that the perceptual system is perfect. It will extract the identity of the object and the pose perfectly, and then we can proceed with that. So that abstraction has issues, and end-to-end training has some clear advantages. So we want to keep the benefits of end-to-end training, and yet we want to have some intermediate representations which transfer over across tasks. So we're going to start to do this by first considering the relationship between perceptual tasks. So even though my interest is really in connecting perception to action, I'm going to start with a story where I'm just considering the relationship between different perception tasks in themselves, okay? And then we'll get to action in a little while. Okay, so I want to start by talking about this work taskonomy. So this is work from a couple of years ago, and the whole taskonomy is supposed to remind you of uh, we have these hierarchies, right? Which normally we deal with, but here we are considering the hierarchies between tasks. So the setup is, how do we understand the relationship between different tasks? So how do we do this? So consider some setting where we have some image, okay, and then from that image we can train zillions of different neural networks, zillions of different functions for computing, let's say surface normals or vanishing point or 2D edges or 3D curvature or etc., etc. So some of these are geometric tasks, some of these are recognition tasks, and so on and so forth. So we have, like, say 20 of these tasks. And a priori, I mean, the traditional approach in deep learning would be train each one of them separately. But surely there is some relationship among these tasks. So consider the task of finding, estimating depth, and the task of estimating surface normals. These two are very closely related, right? Because if you know the depth, then by differentiating the depth, you can get surface normals. But we want a general mechanism. We just don't want to rely on the fact that sometimes we can analytically figure out the relationship between these tasks. So that's the story behind the taskonomy work. Now, here's the big idea. The big idea is, if two tasks are very related, then if I have trained a network for task A, then on top of it, to train a network for task B is going to be very easy. It won't need too many examples. And all you have to do is to train just a readout function on top of the output of the previous stage. If two tasks are very disconnected, then this is not going to help us much. So that's a core intuition. Okay, so I stated this point already, that some tasks we can relate analytically, but some others it's not so obvious what the relationship is. But with this empirical approach, train for task A, can a simple readout function modify this for task B? That's kind of a very general paradigm. And anyway, we go into all the gory details in this paper at CVPR, which actually won the best paper prize there. And the idea is that we have all these tasks that you see here, and we treat them as coming from a structured space rather than as isolated concepts. And there are thick arrows and thin arrows, and basically thick arrows implies that that task is very useful for training the other task. And this is a very practical system. You want to train for a new task, you find a related task, and then you do just a little bit of that, changing the readout function. Okay. So, okay, let me give you one example of building on this concept. So this concept enables us to actually robustify our training of individual tasks as well. So, and here the idea is that you exploit consistency. Okay, so again, going back to the example of depth tasks and normal tasks. So suppose I could train for both of these separately. So I could train in my standard way, one neural network which goes from image to depth, another neural network which goes from image to normals. And in this case, we have trained them independently, but we know that the final outputs have a certain relationship. So therefore, there is some consistency requirement among these tasks as well. And how do I enforce that? So basically, the way you want to think of this is as some kind of a graph consistency, that if I want to get to a certain node in the graph and I can get to it by two different paths, the result should be exactly the same, right? So that imposes some constraints on the representations that have been built up, and we try to enforce that. So, and it turns out that this is quite powerful, and this significantly improves the quality of results. And I should point out that this is connected to ideas such as cycle, GAN, and so forth that have been developed, which are all trying to capture the consistency among different representations that one builds up, except that this is a more complete and general approach. Ideas like this have also been tried in language processing. So I want to build I build let's say a system which translates from English to French. And suppose I have access to a system which can go from English to German or French to German. Then I have an additional constraint, which is that I take the output of the system, convert that to German, take the input, convert that to German, and now these two should be consistent. So that gives us an extra loss. And ideas like this have been tried in the language community. What we have explored here is the generality of that in the context of perception. Okay, so so now let me go on. So this is trying to give you more examples and the benefits of this approach. And the benefits of this approach are that generalization is much better into novel domains, and all that is backed up by various numbers and tables in the paper. This paper you can find at CVPR 2020. Okay, so now I'm going to try to get to action, which is what this workshop should care mostly about, because this is robotics. So we are dealing with the navigation problem, and this is a paper which was presented at Coral 19. So we review, we have a world, an agent, and then there's a policy trained in the paradigm of pixels to talks, critique, brittle, sample inefficient. Okay, so what's going to be our new approach? Now, remember we just discussed taskonomy. So the idea of taskonomy is that there are intermediate representations that are built up for solving different tasks. And these intermediate representations are related to each other. There are consistency requirements among these tasks. If you have trained for task A, it makes it very easy to adapt the solution of that for task B. So all that was the taskonomy philosophy. Okay, how do we apply this for action? So basically, we build up those representations that I discussed earlier. And now what we are going to do is we are going to train a policy for navigation on top of these representations. Okay, that's going to be the approach. So it's quite straightforward. This is essentially like, if for a neuroscientist, this is like trivially obvious. We have a visual system. It has built up all those layers and these different cortical areas, V1, V2, V4, MT, etc. Let's not ignore them. Let's use them. So let's build the action representations on top of those. And we will claim that this will give us various benefits. So to state this more abstractly, we can train from a pixel space, okay, a policy pi, or we get to this representation space phi, and then we train the policy there. And the hope is that training a policy in this representation space should be nicer in some way. It should have better generalization, lower sample complexity, etc., etc. So let's see if that works. So only the policy, not the vision part, needs to be relearned. Okay, so we have this. We have various vision objectives leading us to build up a nice set of intermediate representations. And then the policy is going to be trained with those. And of course, I should note that this is an active vision setting. I mean, if we are studying navigation, we cannot make do with any static data set. We need to have realistic environments. And I refer you to work such as Gibson, which was one of the early pioneering environments in this, and then Habitat. This is work out of Facebook AI research, and this is an environment where really all the engineering details have been taken care of very well. So it enables you to do very, very fast simulations, which is very helpful for reinforcement learning kind of settings. But In these environments, a key philosophical aspect is these environments are captured from the real world. So they're not like synthetic made up game things. So they're real world environments. They are like virtualized reality. And in these environments, where one can move around and get photorealistically accurate renderings. Okay, and then here are our findings. So basic findings are quite straightforward. You train on top of this mid-level system, and with it you get better performance. Generalize is better, and generalization, I'm not going to go through all the experimental details carefully. The generalizes in terms of different domains, different lengths of tasks, etc., etc. And of course, accelerating learning. That's the most obvious part, right? Because when in a pixels to talk task, you're also having to learn the various abstractions for the visual system, which in our setup have been learned separately. And that's shown by this curve that this is how the performance goes up fairly quickly with relatively few examples. It also, not only does it require fewer training cycles, it also becomes much less of a pain. I mean, we all know that RL training is much more of an art than just training a deep learning network for function approximation. There's, I mean, you need some skill, and when a beginning grad student starts out in RL, they have a more difficult time because they have to get all these tricks right. And we find that there is a certain degree of robustness here that you don't have to go around doing a lot of reward shaping and et cetera, et cetera. And the stuff works, generalizes to real world examples as well. Okay, so so this is the first part of my talk, which is basically on how to use vision for robotics. And the summary claim is quite straightforward. It is that we must use these intermediate abstractions, and then do the policy learning on top of those intermediate abstractions. And those intermediate abstractions are going to be good for a wide range of vision tasks and for a wide range of robotics tasks. I'll note this one additional feature, which is that you might think that if you completely fine-tune for a new task, you will get better performance. And that is true. Within the limit of infinitely many examples, using fixed features loses out. But we have a little trick for this, which is side tuning. And the basic setup is that you train a small extra network and you keep the old network around. And this, in fact, enables you to make sure that even in the limit of many examples, you don't pay any performance hit. Okay, so let me take a short 1 minute break, and I will switch to my other talk, which is going to be on imitation learning. So, so I'm now in my second part of my talk, I'm going to focus on imitation learning as a way to make life easier for us. And so I start with this slide, which is on model-free reinforcement learning, and the focus here is on manipulation and this work from OpenAI, and they have this remarkable demo of how to solve Rubik's Cube. And they do a very large amount of the work in simulation, but if you look at the sample complexity, it is incredible. So can we do better than that? And I want to start by trying to say that imitation learning is in fact the way most of human learning happens. So, so think about this historically and culturally. So 100,000 years ago or 1 million years ago, when the early hominids were in the plains of Africa, yes, we had to learn how to start to build stone tools, etc., etc. But today we are talking about 2020, right? We have culture, which is the accumulation of the learning across many generations. We learn by observing others. We learn by observing our parents. We learn at school, etc., etc. So the amount of stuff that you have to figure out completely by yourself is actually a very small fraction, right? You go to, if you are a mechanic, you learn the trade in some workshop working as an apprentice. So it's silly for us to, in AI, to just ignore all of that. Now, this idea has been around for a long time, and this term imitation learning is actually a broad term which includes a whole lot of other stuff. So in the early days, I mean, I have these slides, I mean, going back for in the robotics community, people have tried to do this with more or less just replay mode. So you take a robot through the movements. Okay, suppose you want to get a robot to paint a car. Okay, you just take it through the motions and then you just keep replaying that. So this is just replay of a certain sequence. Okay, this is not going to take us too far, right? Because any complex action you need to, it's going to have a sequence of states, and then you have to respond to the fact that the conditions might evolve, and you need to take different actions at different states. So this memorized replay is not going to work. Now, what makes imitation learning challenging? So imitation learning, learning from demonstrations, I'm using all these terms interchangeably. I personally like imitation learning the best because that connects to the literature in child development more clearly. And it points out that, in fact, there is a fair amount of work to be done in imitation learning. It's not a trivial just replay. And here are some of the challenges. So you want, so in all these settings, we want state action pairs, but we typically don't have access to actions, right? If I'm observing someone, if I observe my parent perform some action, I know the sequence of states, right? But I do not know the sequence of actions, because the actions are in their head, what commands they gave to their hands, etc. We need to deal with the problem of different morphologies. I mean, the human and the robot have different morphology, different robots have different morphology, different dynamics, visual observations. We collect the data from a third-person view, but we have to execute in the first-person view. And very often there might be domain shifts. So I think if we want to really elevate imitation learning to a first-class status, which it deserves to be, because perhaps 90% of the skills we learn are start out as imitation learning. We need to make the underpinnings of this very solid. Okay, so first, so we need to have the ability to analyze human movement, because we're going to observe humans doing some tasks and we need to analyze that. So I'm going to first show you some work we did, which was on understanding 3D dynamics from video. So this is work presented in various computer vision conferences. And the basic setup is we're looking at humans, and this is a video clip of a human, and we have some setup by which we recover the 3D parameters of the human. So the shape of the human, the joint space, what the joint angle is at the elbow and the shoulder, and so on and so forth. So that's what this is. And we actually recover a spatio-temporal representation, which we call a movie. And the way you train this is by losses, which are about predictions in the past or predictions in the future. And I'm not going to get into all the details here, but there's a little clip which will show a bit of the technology, which is essentially the counterpart of a language model. So in languages, you have a sequence of words and then you predict future words. Here we have a sequence of video frames and we try to predict the future video, but in the setting of, not at the level of pixels, but in the setting of the 3D pose of the person. So I'll let this clip play for a little bit.
In this work, we present an approach that takes a video of a person as input and predicts the future 3D mesh sequence of the person. Here, we show the ground truth future video for reference, but the model only sees the input video. To do this, we propose a neural autoregressive prediction model on the latent representation of 3D human motion encoded from the video. This allows seamless transition between conditioning on the past image frames and conditioning on previously generated future predictions. Specifically, for each image frame, we first extract a per-image feature vector. From these image features, we learn a latent representation of human dynamics, which we refer to as a movie strip. Each movie strip is causal, which means that it only contains information about the frames up to the current time step in consideration. We then train a 3D regressor that predicts the parameters of the 3D mesh model from the movie strip representation. This is trained with 3D supervision when available. And if not, the model can be trained with 2D key point reprojection loss, along with an adversarial prior to ensure the poses look realistic. In order to predict into the future, we train an autoregressive model, which is a temporal convolutional network that uses the past movie strip representations to predict the next movie strip. This newly predicted movie strip then becomes one of the inputs to the next frame prediction, which may continue repeatedly in succession. From the predicted future movie strip sequences, we can also read out the 3D mesh parameters. This autoregressive model is trained with the same losses, where the predicted 3D mesh model has to match the ground truth 3D or 2D joint labels, along with the prior. We also included an additional distillation loss, which guides the autoregressive model to predict the actual movie strip representation. Alternatively, we can also apply the autoregressive model directly on the predicted 3D mesh model.
Okay, so I'm going to skip the details more here, but just the point is we can now do predictions of 3D models and generally analyze pose of, okay. So now how do we exploit this for reinforcement learning? So here's an example of an earlier paper. This was in collaboration with Peter Beal and Sergey Levin's group. Here, the idea is that, okay, so we have this video, YouTube video, from which we can now construct this reference motion. So this is what we are trying to imitate. So you only know the state, by the way, right? You just have an observation of the state. So what, now when we train the policy though, what we are getting nicely is a rich reward, because the reward is that at every frame, you know what you are aspiring to be, right? So what you are trying to imitate, if you will. And this is, of course, a policy in a simulator. And the advantage of that is that you can, it's a physically correct simulation. It's a policy. It's not just a running through. And therefore, you can be robust to, let me see if I can show this demo. So you can be robust to various kinds of manipulations and so forth. And I mean, this is a paper from a year or two ago, so you can look there for all the examples. Okay, so now I talk about some more recent work. This is just very recent and it's out on arXiv. This is trying to tackle a harder problem, which is dexterous manipulation. So dexterous manipulation is manipulation with your hands. And this is a much complex high-dimensional action space. And there are now various techniques out there. So this Rajeshwaran et al. Paper is the one to read, where you use a combination of sort of VR glasses and motion capture gloves to have humans perform some task, some manipulation task like twirling a pen or whatever. And then we are going to try to train a robot hand to do this. Okay, so the contribution of this work is how do we manage if we have access only to states? So this is the setup. So traditionally in demonstrations, you want to have state action pairs, right, for training a policy. Now, if I'm the third person observing somebody, all I have is the state, right? I know their joint angles. I cannot know what action they commanded. I do not know their neural commands for the various joints, the torques that they commanded for the elbow and wrist and so on. I don't have that. So I only have access to the state. So this is the practical problem if we want to learn from video of anything, manipulation, navigation, whatever. So the manipulation case is the harder case, but we need to solve this. So how are we going to solve for this if we don't have access to the actions? So the secret is, let's build an inverse model. So if I have a sequence of states, then I can build a model which says what is the action which would take me from state S0 to state S1. Okay, and there's a line of work on this going back quite a while, and the work from our group was this work by Pulkit Agrawal on learning to poke by poking, which was at NeurIPS a few years ago. So there's inverse models, so train forward models and inverse models. This is a very, very good idea. It's an old idea, but it's worth rehabilitating it and exploiting it. So, so big picture, I'm running out of time, so I'm going to end quickly. So there is the usual, so when we are trying to train a task, we are going to have the usual RL term and an additional term which corresponds to the imitation, and you're going to anneal that to 0. So you see there's lambda 1 to the power k. So the idea there is that over time, the importance, the imitation just gets you in the right space to begin with, and after a while you just have your standard RL loss. And this imitation term, you need to know what actions to perform, and we find those actions by using the inverse model on the observations that you collected in imitation. So you collect trajectories from the policy, update the inverse model, predict actions using the inverse model, update the policy. And here are a variety of tasks. So moving objects around, in-hand manipulation, opening a door, tool use, and this is these are the results. So basically, so this is the important slide. So in yellow, the lower bound is if you don't have any demos. So pure RL training, no imitation. Okay, and that obviously it learns, but it takes much more time. Okay, the two top curves, the blue curve and the red curve, those are the ones which are of interest. So this DA is a sort of demo augmented policy gradient, and that has access to both the state and action. So that's that should do the best, right? And the SOIL, state only imitation learning, is our contribution. And here the idea is that we don't know the actions. We are going to learn this inverse model as we are going along, and then we are going to use that to predict the pseudo action, if you will, which we are going to try to match. And if you look at those two curves, they're pretty close to each other. So what that says is that we don't need to have access to actions, and just from the state, we can do imitation learning. So that's the bottom line, and there's lots of details to make this work, and those are in the paper. And there are some other findings, which is that, yeah, so these are just demos of the tasks. It generalizes to different kinds of morphologies, like 4-finger hand versus 5-finger hand, that kind of thing, as well as some changes in the dynamics. So you change the mass of the objects, and does it still work? And I think you trained on picking up cubes, and now you have to move bananas, so things like that. So I'll end here, and the bottom line here is that what are we after? What we are after is this grand goal that we make imitation learning first-class technique. And eventually what we want to do is just exploit YouTube videos of people doing various actions. The vision system extracts pose and so forth, and trajectories of pose. And then with the technologies that I'm describing, we are going to be able to do the manipulation task. Now note, this task is still in simulation, so there are obviously challenges ahead still, but I feel that this is a very promising direction. Thank you very much.